In a recent post, we shared an AI-generated guide describing how to use the Point Source Microscope, or PSM, for alignment of off-axis optics using aberration analysis. While AI apps are amazing in terms of what they can do, this information is vastly outdated. We demonstrated a more direct and quantitative method over 5 years ago in a video illustrating alignment for using a Bessel beam for cemented doublets. The same principles illustrated in the video also apply to tabletop alignment and off-axis optics. Rather than interpreting aberrations, the method in the video defines the optical axis of the lens using two spatial references, a Bessel beam projected upward through the lens or optical system, and a return reflection from the center of curvature of a surface in the system illuminated by the PSM. In the video, the PSM is first adjusted so its focus is at the center of curvature of a concave surface and centered on the Bessel beam projected up through the lens seat. As the lens is inserted in the beam, the PSM captures two spots in its field of view, a bright solid spot from the center of curvature and the core of the transmitted Bessel beam along with its rings. The lens used here is the meniscus half of a doublet constrained laterally by the circular seat. As the lens is tapped into position, both the Bessel beam and the center of curvature spots move in a combined tilt and decenter of the lens relative to the optical axis of the fixed Bessel beam. Because the lens surface in contact with the seat is mechanically constrained in translation, this degree of freedom must be adjusted separately to get both spots centered on the PSM crosshair, indicating the complete alignment of the lens optical axis in tilt and decenter. Once the seat is aligned, centering subsequent meniscus elements is highly repeatable. The convex surface is simply slid on the fixed seat, bringing both the reference spots into alignment with the PSM crosshair. Although the video is not an exact analog of alignment of off-axis mirrors or lens on a tabletop, the principle defining and matching a reference axis via two spatially separated datums is broadly applicable to many alignment situations. The technique is especially powerful because the Bessel beam propagates like a single optical ray, analogous to a geometrical optics ray propagated via ABCD matrices. The method facilitates rapid alignment to a single micron and second of arc precision without having to move any part of the measurement apparatus. This makes the process rapid and precise.